My name is Blakesley Burkhart, and I am associate research scientist at CCA and jointly appointed at Rutgers. And yes, I've put my appropriate symbols on my title slide here. And I'm really glad that we watched that safety video at the start of the morning because it's about to get a little turbulent. So buckle up. I know, really bad. Sorry. So I am interested in more diffuse forms of turbulence than we heard in the morning, in particular, fluid problems related to magnetic fields and turbulence that touch on the interstellar medium of galaxies. And I love showing this cartoon because it kind of ties in together different problems that I think about and have worked on in the past and am currently working on, as well as touches on a huge range of scales that fluid turbulence affects. So, of course, the dynamics of stars, as we heard about in several talks this morning, which is a big active area of research at the CCA, but also many areas in ISM, in galaxy physics, and even in planet formation and disk formation. So a few things that I've been working on lately that I'd like to tell you about is more related to star formation and galaxy formation. So star formation theories are a complete mess, in part because they deal with turbulence and fluid dynamics and the complicated relationship between gravity, stellar feedback, turbulent motions, and magnetic fields, but also because we don't really have any proper analytic models that tie together all the huge ranges of scales. And so this is something I've gotten really interested in recently in terms of trying to combine what have been called in the literature top-down star formation models, which take into account the dynamics of galactic disks in some sort of equilibrium in terms of their vertical force balance and their energy balance. So those would be called top-down models, where you take a whole disk, and then tying those together with what are called bottom-up models, which start with the physics on the GMC scale and how that connects to star formation efficiencies and the IMF, which are properties of star formation that seem to be somewhat uniform and universal over redshifts. And so the two models that I am considering here, one is the top-down model where myself and my collaborators, including John Forbes, who's now here at the CCA, have been working to combine feedback from supernova and transport from gravitational instability and mass flow through a disk. So this is the first model that combines both the energetic input of the supernova as well as the mass transport. And so this model is very simple in a way, even though this flow chart looks somewhat complicated, in that our assumptions are gravitational instability, so we require a Toomre Q of about 1, vertical force balance, which sets your midplane density, as well as energy balance. And the energy balance takes both a supernova feedback rate, which is tied to our star formation rate, as well as a gain term from transport and torques from gravitational instability. Both of those two terms then go on to set your gas velocity dispersion or your turbulence level, which can be used to describe observations. Which is what I'm showing you here. So these are observational data points of the star formation rate and the velocity dispersion in a number of galaxies, both at low redshift and at high redshift. And this plot here that it's set in is actually results from the illustrious TNG simulations, where we're plotting each individual halo's star formation rate and gas velocity dispersion. And the models are able to predict both this flat regime here as well as this corresponding rise that we see in the high redshift systems. This is not enough, this is not good enough, because we're still making assumptions about the efficiency. And that's where we're able to bring in the GMC scale models like Sabrina was talking about earlier in order to tie all these different scales together to make a unified model of star formation. And if you happen to be on the NASA TAC, that is exactly this proposal. So watch out for that. A few other things I'm working on this year at CCA. I'm collaborating with David and Mike Shelley at CCB in order to create a combined meeting for turbulence that will look at research being done in the field of turbulence across a huge range of scales and also disciplines. So biology, atmospheric sciences, astrophysics, and mathematics. And so it's going to be a very exciting meeting that's drawing together researchers from all over those fields. And that's happening December 2nd through 6th, and the registration page is open. And then finally, talk to me about space cats.
Thank you, Blakesley. Unfortunately, we don't have time for questions, but you can find Blakesley at the CCA anytime. Miles, you're up.
My name is Miles Cranmer. I'm a graduate student at Princeton working with David Spergel and Shirley Ho. Over the past year, I've worked a lot with neural networks, which are this very flexible machine learning model. And I think they're both overused and underused in astrophysics. I think they're used a lot when a simpler, more interpretable model could be used. And I think they're also underused because they can be applied to so many different problems, and it's just not obvious how to do it yet. So I'm going to talk about two projects I've worked on over the last year. So one thing you should know is neural networks, they're not just for classification or regression. I like to think of them as a programming language that you code with data. So they're very flexible both in what they can learn and how you structure them. So the first project I worked on, we use what's called a normalizing flow. So this is it's a neural network where you divide it by its own Jacobian, and that normalizes it, so you actually get to model probability densities. So we learned the color magnitude diagram of Gaia and use that as a prior to improve the distance estimates. The next project I worked on is it involves graph neural networks. So if you have a data set that's better structured as a graph, so like particles and the edges being forces, that's graph structured data, so you want to use a graph neural network. We showed how you can apply this inductive bias to make it learn an interpretable representation. So in this example, it learned to predict Newtonian gravity simulator, and we actually extracted Newton's law of gravity from it using symbolic regression. So it's a very interpretable way of learning on a graph. So my long-term lofty goal, it's like a 30-year goal. I'm very interested in automation. I want to automate large parts of astrophysics, and of course, machine learning is the way to do this. Over the next year, I think the stepping stones toward this goal are these. So I'm interested in merging data-driven and physical models. And I'm also interested in machine learning for astrophysics theory. So these are some new projects I'm working on. Feel free to talk to me about any of these, particularly Bayesian neural networks. So these are this kind of neural network architecture that's provably equivalent to a Gaussian process, even though some people don't want to hear that. And I also do probabilistic machine learning, work with Gaia data, graph nets, and normalizing flows. So feel free to talk to me about any of those. And I have a lot of time for questions, which I wanted. So, yes.
Graph structure work with inferring Newton's law better than any other neural network architecture? It doesn't seem something that has an obvious graph interpretation.
So the graph structure data, in this example, it's an n-body simulation. So the nodes in your graph are particles, the edges are the forces. So it has to learn kind of the messages that the nodes pass. And so traditionally you use this for any kind of network-based data set, but we basically we applied it to the simplest possible physical example, this planetary system, and it learns the simulator. It learns to simulate Newtonian mechanics. But what we did was we minimized the messages, and it basically, we learned that it forces the graph neural network to learn interpretable representation. And then the second step, we apply this symbolic regression, so it's kind of learning a symbolic equation that represents your neural network, and we extract Newton's law of gravity. And that's applicable to, there's no prior information in that. You can learn an algebraic expression for any graph, basically. Yep.
Okay. Okay. So for this example now, you said that the edges are forces, but why not distances? Why not make it something more, physically
So
fundamental?
it learns that. So all you give it is, in this example, you give it the mass, position, velocity,
Okay. Okay.
and you can also give it edge-specific attributes. So you could say it's a 1 if it's a gravitational, 2 if it's electromagnetic, and it would learn to switch between the forces.
Okay.
But it's a very generic architecture. It'll learn distances and learn, like it learns this,
Okay.
and then we kind of rip it out and
Okay.
interpret it. Yeah.
Okay. Great. Thank you.
Okay, we're out of
Cool.
time.
Let's thank Miles again. Adria Price Whalen.
Thank you. So I'm a postdoc here now. Okay, so galaxies grow. You know what? I'm going to use this big stick. Galaxies grow hierarchically. So smaller galaxies, as they orbit larger galaxies, like any of the ones that I'm showing here, are disrupted tidally, usually by the host galaxy potential. And so this happens to satellite galaxies, to globular clusters, anything that's orbiting around, and as they are disrupted, they leave behind debris. So you can see this tidal debris around this some distant galaxy here from the HyperSuPrimeCam survey. You can see it around our neighbor M31, and you can see these stream-like features in the halo of our own galaxy, the Milky Way. So in this way, the sort of stuff that's disrupted ends up leaving behind in stellar halos a fossil record or sort of a graveyard of debris of things that have merged with larger galaxies. And we see this universally, as I mentioned before. You see it all around the universe. And so using these things, these structures, these streams, these shell-like features, we can obviously then use them like fossils to infer history. We can learn about when things were accreted, how massive they were, etc. But I'm more interested in using these sort of as secondary tracers, because you might notice that these streams trace out what look like orbits at very large distances from their host galaxies. And that orbital information we can then use to understand the properties of dark matter on very large scales. Boop. So in particular, I'm most interested in using these tracers around the Milky Way, our own galaxy. So in the Milky Way, we know of between sort of 40 and 60 of these stellar streams, depending on your threshold for believability, I would say. This is one of my favorite ones. This is sort of the best known stream, best studied stream, circa 2010 or so. So this is showing in sky positions. This is rotated to be oriented with the stream. Just stellar number counts of stars that are filtered to be in this stream, which has this funny name, GD1. A lot of things have changed in the last year. So one thing that happened is Gaia released data release 2, which gave us proper motions, kinematic information for a huge number of stars all around the Milky Way. And with this data, myself and collaborators like Anna Bonazza, we've been using the Gaia data, going back to the streams that we know about, to try to produce much higher contrast views of the streams, like this GD1 stream. Using this higher contrast data, we've then been able to more precisely characterize the distance and internal properties of the streams. We've also found some interesting surprises. So this plot came up earlier from David Hogg's talk. This is a model of this very thin feature, this what we call the spur around GD1, where we think that this is an indication of an interaction between a very dense perturber, a massive perturber around the Milky Way that flew through the stream and produced this sort of offshoot of material. So the streams are both sensitive to sort of the large-scale distribution of dark matter, but also to very thin local events like this. So since then, we've been looking at many other streams. So GD1 is just one of those 40 to 60 streams that we know about. They all have interesting names, like Jalum, Palomar 5. And one of the things we realized is that none of the streams are very simple dynamical structures. And that complicates this goal of using them to understand and constrain dark matter, because they all have their own sort of intricacies, like strange wide substructures that are around the streams, or asymmetries between the tails. And so the question then that we're working on now is, of all of these peculiarities, which of these things are weather, interesting but local dynamics, and which of them are fundamental? Which of them can we relate back to dark matter? So I primarily work on building and improving models of streams, and then using analysis methods, data analysis methods, to infer properties of dark matter. I'm interested in many other things, so come chat with me if you're interested.
Time for a quick question. Let's do Mehmet.
Give it a sec.
All right. I was just curious, do you have a handle on when the interaction with the spur to create the spur happened?
Depends on many different things, but probably within the last giga-year or so.
Amiel?
Streams still have a piece of the progenitor attached to them.
Well, Palomar 5 connects back to the host globular cluster, which is also called Palomar 5. Most, I would say, of the other ones do not. They just look like these funny, long distributions of stars.
Yeah, thank you.
Let's thank Adrian again. Yeah.
Hi, my name is Aaron Young. I'm a graduate student at Rutgers and mostly here. What I'm about to tell you is an overview of everything I do, and if anything I mention that interests you, please come talk to me. I'm usually on the 6th floor. So for my thesis, I've been using the Santa Cruz semi-analytic model developed by Rachel for years to make predictions for galaxies at high redshift. So because the model is very efficient, I can do controlled experiments and understand how the underlying physical processes would impact the predicted galaxy properties for galaxies over a wide mass range. And to take this further, I also added a reionization model to the pipeline, so I can do all sort of fun experiments with it. And a lot of my work, most of my work are advertised under the banner of semi-analytic forecast for GWST, but this is not only for that one telescope, but also for everything that comes beyond it. So I'm currently working with the GWST Cosmic Evolution ERS team, and also the W1st Cosmic Dawn Science Investigation team to make these predictions. But if you're excited about this telescope, please come talk to me too. But while these amazing telescopes are sitting on the ground, I'm proposing the next project called Samurai, which stands for Semi-Analytic Model with Ultra-High Redshift Astrophysical Interplay, which is an umbrella project that I'm hoping to add a bunch of exciting physical processes to the SAM to make more robust predictions at high redshift to get ourselves prepared for the next 2 decades or more. So for observers, please come talk to me if you have any things that you want me to make predictions for you to help you. And for theorists, the special request is please come tell me what physical processes should I be adding to the model. I'm still looking for ideas. And I'm at the job market, hint, hint. This is everything you just heard is a preview for a talk that I'm about to give next Thursday at lunch. So if you're around, please come to my lunch talk. That's it.
We have plenty of time for questions. Catherine.
To Samurai. What are you going to put into Samurai?
I'm glad you asked. So the biggest idea that Rachel and I came up with is I'm hoping to put in the coevolution of the first star and the black hole seeds. I think these are going to be super important to properly model galaxies at very high redshift. But I'm also proposing a separate project that will go in parallel. It's called GRAFT. So we're going to explore the formation of dark matter halo at high redshift, and the word graft is chosen as in grafting in gardening. So you can graft different branches to form new species of tree, and it spells GREFT. It reads gadget at ultra high redshift with extra fine timestamps. Yes, I love acronyms. Hi, David.
Chiara.
Can you say a little bit about multi-messenger signals potentially? Sorry, that says multi-instrument, but I automatically read
No
multi-messenger.
worries.
But the question still stands. Do you have any
Yes.
multi-messenger work?
Right. So some predictions will be also made for ALMA using work from Gregor Popping. So we explore emission from molecular gas and also nebula emission from high redshift galaxies, and hopefully get some nice spectra for predicted for future telescopes like Origins. And Lisa, yes. Thank you, Rachel.
David.
So right now for W first, we're planning an ultra deep field. And the idea is to do something that is multi-instrument, to get a target field and get LSST, radio, X-ray, get as many telescopes as possible to point at this field. It'll probably be the first thing that W first will do. Actually, maybe spend 2 weeks to a month going deep. So, well, first just to advertise that to you, because it sounds like a really useful set of tools for making predictions for that. But one of the things we have been doing at the AAS meetings, and we'll probably continue for the next couple, is have community meetings to discuss what do we want. So, I mean, if you've thought a lot about that immediately, the question is,
Am I invited now?
it's AAS meeting.
Okay.
You've been invited to every,
I can just go in and
just
crash the
go
meeting.
in. Right. The idea is that this is open to everyone.
Okay.
And but since you're one of the people thinking deeply about this, that it's worth thinking about, and maybe you've already thought about, what would you want from an ultra deep field in terms of multi-wavelength? What is it important to get GRISM data on it? How should we proceed?
Thank you, David. I'm so crashing that meeting.
Let's thank Aaron again. Next up is Stephanie.
I have no idea if I'm sticking to my time limit or not. Okay, I make no promises. Okay, yeah, so once again, I feel like I may have made a somewhat incomprehensible 4-minute talk. So if you are interested in any of the words that you hear, please come and have an actual conversation with me later. I would really like to discuss any of this. So I'm an ARS at the CCA. And one of the topics that I'm really interested in are RAM pressure stripped galaxies, which are galaxies that are moving through a cluster and interact with the intercluster medium. And so the stars are unperturbed, but the gas is removed from the galaxy, kind of like when you're riding your bike really fast and the wind blows your hair back. Not only can we think about RAM pressure stripped galaxies in terms of galaxy evolution, but we can actually really understand a lot about gastrophysics when we look at the tails of stripped galaxies. For example, here is a tail that's observed in Virgo, and you're seeing contours that are showing you a H1 tail that's 100 kiloparsecs long, being stripped off of this galaxy. And so one of the questions is, how does this neutral, cool gas survive to such large distances? In the same cluster, we have another galaxy, and this is being observed in H alpha. And so you can see a very long tail of H alpha emission. And so then the question is, why is this gas that should be cooling or heating very quickly surviving out to or being formed out at these large distances? We can also look at H alpha and actually find star formation in stripped tails. This is about 20 or 30 kiloparsecs off of a stripped tail, and each one of these kind of green clouds is a star-forming region in gas that's been RAM pressure stripped off the galaxy, also observed in H alpha. And then we have one of the most famous, currently anyway, galaxies that's been RAM pressure stripped, ESO 137-001 in the Norma cluster, and in blue you can see this Chandra image of the X-ray gas, so really hot gas. And in red, you can again see H alpha emissions. So you can see some H2 regions and some very different structure in the different temperature gas. And so one of the questions you can ask is, how do all of these different gases mix? Where is heating happening? Where is cooling happening? How much of this is due to different ICM or galaxy properties? How much of this is due to the different wavelengths that are being observed? And so this is a simulation of mine, and in the top here you can see kind of X-ray emission from a stripped galaxy, and then in the exact same time step, this is the cold dense gas. And so part of the question is just exactly what gas are you looking at in any given time. So your cool gas is going to have a little bit of a different morphology than your hotter gas. But you can also take a look and try to really understand in different scenarios, so different ICM pressures, temperatures, densities, velocities, are you getting different properties from your tail gas? And you can also ask kind of specific, interesting questions. One of the mysteries that's currently being considered is, why do you have star formation in stripped gas? Is it because, for some reason, really dense clouds of molecular gas are able to be ram pressure stripped from a galaxy, which would be surprising because they should be tightly bound to the galaxy? Or are you able to form star-forming regions from more diffuse gas that's been stripped from the galaxy? And so one of the things that I've done is I've looked at a simulation and I've identified clouds at a few different heights in a tail. So we're looking at 10 kiloparsecs, 70 kiloparsecs, and 160 kiloparsecs. And then I can compare properties of these clouds to try and really understand, what's going on. And I'm not going to tell you why. You have to come talk to me. But it is due to, they are being formed within the stripped gas in the tail consistently at all different heights in this, in the stripped tail. And so it is not from really dense clouds being stripped. I'm going to take my last moment to say I'm really interested in a lot of different things, though, not just ram pressure stripping. This is a simulation. I'm going to start working on something similar where I'm including star formation to, again, look at star formation in stripped tails in the next couple weeks. This is some work that I'm doing with that's led by Miao Li, who's a postdoc. Oh, my gosh. Who's also a CCA'er, and she's not here, so I'm going to highlight that. And then I'm looking at galaxies. These are real galaxies. At real galaxies. But then I'm also looking at for analogs in illustrious TNG with Chitska Starkenberg, who is also not here. And I even think sometimes about abundance matching. Sorry.
Thanks, Stephanie. Next up, John Forbes.
Hello. So I'm new here. So I'm starting at the Flatiron Institute in a couple weeks as a postdoc. And so I guess by way of introduction, I wanted to show you just like all my papers as a function of scale and time that they were published. The shading means I wasn't the first author. So yeah, I'm not sure yet whether I'm like a galaxy person with some side projects or like a theorist of a jack of all trades. But yeah, but I'm going to talk to you about galaxies right now. Yeah, so this is a project I've spent a lot of time on in my postdoc. So the idea is it's a semi-analytic model, just like Aaron discussed. This is a real galaxy, and I've drawn some concentric circles on it to emphasize that this model resolves galaxy into radial bins, and we simulate the gas moving around, gas accreting, gas forming stars, all that stuff. Our basic philosophy with this is sort of the kitchen sink. Put as much physics as we think might be important in the evolution of galaxies into the model as we can. But of course, since it's a 1D model, we end up with a lot of parameters. So these are the ones that are used in the latest work. And the real key of this model, the reason, the thing I've been working on sort of the longest since grad school is this part, the disk transport, where this is sort of related to the model Blakesley mentioned, where we one of the ways we can move gas around in this disk is via gravitational instability dominated transport. But we're flexible. There's an alpha disk as well. Anyhow, so I'm gonna show you one basic result from this work. So we were looking at this parameter, the mixing of supernova ejecta with stellar winds. And so the first thing we had to do was actually, so this is a 1D model, it's a little bit expensive. So to actually do this sort of thing, compute Bayesian inference on these parameters that we're interested in, had to build a neural network to basically map the input parameters into the output variables that you can actually observe in a sample of galaxies. So most of what my time was spent doing was getting this to work well enough to give us a quick way to get from the physical variables to the observables, and then do some Bayesian inference. And the result of that inference is what I'm showing here, one example. So this is the distribution of this quantity, which represents how metal enriched the winds are. So the winds can either be, so it's parameterized this way. I'm not sure other people use this parameter, but I think they should. It basically, I have to make this stick a little shorter. So the winds can basically be the same metallicity as the disk, or they can go up to some maximum metallicity. That depends on how much metal you're producing in supernovae, and that's controlled by this parameter, which can be anything between 0 and 1. Usually people assume it's 0, hence why my prior peak's at 0. But the model really prefers to eject lots of metals. And I think this is also borne out in observations, but I'm working that out now. But I think this is sort of the most surprising result. And with that, I will stop.
Ben.
What was your smallest scale paper about?
So that's about Bdello-bacteriovorus, which is a natural antibacterial predator, which is itself a bacteria. And they needed someone to estimate drag forces of these critters in various formulations. I think you might win the smallest.
Subatomic. Yeah.
Mordecai.
Why were you surprised that the supernovae ejecta, which are shocked to high temperature, are efficient at taking metals out of the galaxy brought in by the supernovae? Why was that a surprise?
That's a fair question. I mean, I think it's just because as an analytic modeler, people use 0 all the time. So I'm just biased by the previous work in the field. But I mean, you're right. Physically,
has always ejected many metals.
The issue is, we're not even sure that it's supernovae predominantly driving the winds. To be a little controversial. So, I mean, it just depends. Like if you have very large mass loading factors, you imagine there's a lot of mixing. So it's kind of surprising that they're still managing to be this metal enhanced.
So I'm afraid that's all the time we have. Let's thank John again. Next up is Savik.
Hi, everybody. So I'm Savik Ford. I'm a professor at CUNY. I'm also a research associate at the American Museum of Natural History, and I even spend some time here helping to coordinate some of the summer student programs as part of Astrocom NYC. Today, I'm going to make a very strong claim, so I hope there will be time for questions. I'm going to make the claim that the GW 1907-06 event happened in an AGN disk. For those of you who are not super up on all of these phone numbers, this is also known as the most distant detected gravitational wave event by LIGO Virgo. It's at a distance of about 5 gigaparsecs, which is nearly a redshift of 1. I do just want to also highlight that I work on this with a lot of people. This is not even everyone who's in my group, but this is everybody who showed up for the photo this day. Some of them will be giving posters and talks at future Gotham fests. And so you can come and bug any of us. If you'd like to attend our group meeting, we would be more than happy to have you. It's in Mordecai's office at AMNH, but you can email me if you want to get on the list to come visit for any reason. Okay, so to my argument, and also for those of you who have trouble keeping track of all of these horrific phone numbers, it was suggested to me that I should give this thing a name. This is a completely unofficial, unsolicited, unverified. I just named it with the help of some people at lunch. We're going to call it Frida because it happened on Frida Kahlo's birthday. And that is all. So now we can keep track of this thing. And this is the source. This is the distance from GraceDB. And you can see that it is really far away. And so, because it is really far away, in order for LIGO to have detected it, it must have been banging loud, which means that it must have been fairly massive. And I can say that it was probably at least 150 solar masses. And what that means is that the progenitors that went into it were both over 50 solar masses, or if you think that it was a substantially unequal mass ratio, then obviously one of them had to be very much more than 50 solar masses. And that means that if you believe the stellar evolution people, or at least what they said before this event was detected, you can't make those things out of direct stellar evolution because of pair production instability. And so these progenitors themselves were the product of a previous generation of mergers. That means that since you expect a kick from that previous merger, those objects would have escaped from any potential that had an escape velocity of less than 50 kilometers per second. This is not the first time that one of these has been seen, but it is the first time that both things had to be way over. So there's a previous event that might have been a triple that was looked at by Juros and Birdie. Just to point out that if this is a hierarchical merger, then a huge fraction of the mergers from LIGO that are at the lower mass end must also come from the same channel, right? You have to, in order to get up to this high, there have to have been many mergers that went in that don't lead to something this large directly. So this is just the tip of the iceberg. So given that 50 kilometer per second limit, you could say, okay, it happened in a galactic nucleus. Congratulations. Why do I get to argue that it's an AGN? Well, I would refer you to some of our previously published work, but also, I want you to remember what the nearest galactic nucleus looks like. These are the stellar orbits, of course, around Sag A star, and you can see that they are dynamically hot. Stars and stellar mass black holes that are in our own bare, relatively gas-free nuclear star cluster do not like to form binaries. If they form binaries, they don't like to stay in those binaries. Most of the collisions that they experience are going to be disruptive and ionizing, and so they are never going to have the opportunity to merge. Despite this fact, there are plenty of stars that have, for example, pericenters in the region where you would expect an AGN disk to form. And we expect, in fact, that there are on the order of 10 to the 4 stellar mass black holes hanging out in the neighborhood of Sag A star. If you go ahead and you drop a gas disk on them, you will provide a preferred plane of orientation. You will provide a source of dynamical cooling. And so the orbits will be damped. They will tend to be circularized. They will tend to become coplanar. Binaries will tend to be driven towards each other and form new binaries. And so the one big takeaway of my talk is there are things in these disks. Things may cause a lot of other interesting effects that should be taken into account. Thanks. Oh, and we predicted this way back here.
Let's thank Savik. No time for questions, unfortunately.
You know where I live.
Francisco? Great.
So all this very long list of characters is my name. People call me Paco. So I'm a postdoc here. I'm leaving now to Princeton next week. So I just want to very briefly tell you about the kind of vision, for me, a dream that we have been developing with David, with Shirley, Ben Wander, but also with all the other postdoc, graduate student, undergraduate student, and also high school students. So what is this dream? So basically what we want to do is to extract every single bit, and this is a long-term vision, every single bit that is of cosmological information that is in cosmological observation. So what is the idea? So the idea is to create the most realistic observation that we can and basically train a neural net in order to go directly from the three-dimensional density field, or whatever thing that you have there, directly to the parameters. And the reason for this is basically because it's mathematically impossible to know what summary statistics in case there is something that will give you this. So, and once we have trained this network using simulation, we are going to take real data and just get the value of the parameters. And with this, we are going to get, in principle, what is the nature of dark energy, the sum of the neutrino masses, and all the fundamental physics that we want. So how are we going to do this? So we are going to need thousands of cosmological simulation, gigaparsec boxes at least. Training these neural nets takes a lot of data. These are going to have to be high-resolution simulations because the galaxies tend to live in small halos, but also for things like neutral hydrogen, we have to go all the way to 10 to the 9 solar masses. We are going to a smaller scale where most of the information is. So basically, we also need we need full hydrodynamical simulations. And because we don't fully understand baryonic physics, I think the best thing is to marginalize over this. So we are going to run simulation with different baryonic physics and basically train the network to marginalize over this. And finally, we need very deep neural nets in order to basically find the mapping between the 3D density field and directly the parameters. So let me first talk about the thousand of simulations that we need. So I think this is done. So for more than 1 year, we have been running this simulation. This is what we call the Quixote simulation. So I think this is the largest set of M-body simulation ever run. Everything done at CCA. So yeah. We have 43,000 full M-body simulation. We have more than 7,000 cosmologies. This is the hyperplane that we are looking, basically the most important cosmological parameters. We have a really, really large volume. So yesterday I was computing the comoving distance to the CMB, and it's only like 10 gigaparsec. I don't know if I make some error, but it's only 10 gigaparsec. So what this means is that basically the volume of the whole universe from redshift 0 to the CMB is only 1/10 of the volume that we sample in this simulation. So we have really a huge volume. What else do we have there? So we have a lot of particles. We have trillions of particles, and this is only a redshift 0. We have almost 10 trillions of particles. We have billions of halos, billions of boys, and we have millions of summary statistics, Pago spectra, bispectra, PDF, and all these things. So we have spent more than 35 million CPU hours, and again, CCA resources are amazing. We have produced 1 petabyte of data, and next Friday we are making everything public available, so everybody in the community can use this. So from this side, I think we are done from the 1,000 of simulations. So this simulation, of course, we don't resolve very small halos. If we have run simulation with higher resolution, instead of producing 1 petabyte, we will have produced 100 petabytes, and then we will not be able to store this. But we can use deep learning also to increase the resolution of the simulation. And this is something that we are doing with our colleagues in Paris. So basically the idea is that you take the redshift 0 output, and basically you take the high resolution simulation, the initial conditions, and basically you join the two things, and you are able to produce the high resolution redshift 0 output. And this is using deep learning, so you don't have to run the simulations that are extremely expensive. Baryonic physics, again, is super important, so we should not forget about this. So this is something that we are doing with Daniel and with Shai. So we are running full hydrodynamical simulation. These are state-of-the-art, the SIMBA and the Illustris TNG project, with different cosmologies, but also different astrophysics, and also more than 1,000 simulations. And because we are going to have the embodied, we can find the link between dark matter and full hydro. And finally, we need this very deep neural net. So this is a work that Anna, who is an undergraduate student, has been doing, and basically you can see her poster so far is working well, but there is a lot of room for improvement. And yeah, so this is our dream. Thank you.
Questions? Yes.
Yeah, this is super impressive, and I like that you are marginalizing over the baryonic physics, but do you still need to use the assumption that one of the implementations is correct? Or?
Very good question. So no, so what we are doing so far, and I have some preliminary results, is we are training the neural nets on this simulation on SIMBA, and once we have trained the neural nets on this, we are being able, if we are able to predict these parameters. So what we find is that for cosmology, we are able to predict this, and for astrophysics, no, because the astrophysics is completely different implementation. But for the cosmology, a redshift 5 is working. So it's somehow learning to marginalize over this.
Let's thank Francisco again. Next up is Glennis.
Thank you. I'm Glennis Farrar, and I'm at NYU. and I do a bunch of different things. So I'm going to mention, I mean, they're listed there, and there's some more on the bottom, including tidal disruption and things. But what I want to talk about, wrong place. What I want to emphasize right now is work on the galactic magnetic field, because I think it's the least known probably, and it connects to pretty much everything anybody's doing, at least 90% of you, and I hope you'll come and talk to me about it. The purpose of this slide is really to remark that this Janssen-Ferrar magnetic field model of the galactic magnetic field, which dates from 2012, is still the leading galactic field model. It's hundreds and hundreds of papers cited. You ask, why is 7 years gone by and nobody's improved it? And so that's what I want to talk about, and then tell you about improvements that are coming in the next month or two. A point that I'm going to make now, I guess there's not a pointer here, but the basic data is rotation measures, all sky. This will work. It's low enough. Pretty much all sky rotation measures, this has now been filled in, and synchrotron emission, the Stokes Q and U, and also the total intensity. The problem is, that they also depend on the electron density and the cosmic ray electron density. So when Ronnie and I did our work, we just used the best available models. But now we know those models are really not very good at all. I mean, it was sort of clear they were likely not to be oversimplified, but that was all we had. First look at the upper right hand, and that explains the 7 years. The reason it's so tricky is that actually for instance, the cosmic ray electrons, that's partly what you know in the turquoise square, you have to have that in order to interpret the Stokes, or the synchrotron emission, IQ and U. If you knew those two, that gives you good information on the magnetic field. Not complete, because the longitudinal magnetic field you can probe with the rotation measures if you know the electron density. But for example, to get the electron density, let me focus right now on getting the cosmic ray electrons, which is even more challenging, which I think we've solved. You need to know how they lose energy. Well, how they lose energy depends on, you need to know the three-dimensional distribution. It's constrained here, having passed through the magnetosphere, the heliosphere, by satellite data. But we need to know it throughout the galaxy. And so it depends on the diffusion coefficient, that's the D in the diamond shape. But the diffusion coefficient is constrained by measuring the boron to carbon ratio. The boron to carbon ratio depends on, anyway, you see how totally interconnected it is. So, actually I'm doing okay with time. I could give a few more examples. In order to predict for example, explain or try to predict the synchrotron emission of the galaxy, you need to know specifically the cosmic ray electrons and their energy distribution, because, for instance, if you're interested in predicting the background to cosmic dawn kinds of experiments, or to interpret, to get the foreground for CMB missions like Planck and so on, then you need to be able to model that well. The best information comes from what's the so-called Haslam map, which is much lower frequencies. So you need to know the spectral index of the electrons throughout the galaxy. Anyway, this I'm very proud of. I have to show off. This is our model that explains the Haslam map, and that's the map. With that, we can predict the CMB, that is the synchrotron emission contributing to Planck, including the polarized synchrotron emission. As an illustration of how well we do predicting the electron spectrum that's measured by AMS, for example, the lower part on this side is the high energy stuff where the corrections from the heliospheric magnetic field aren't important, and the Voyager data is measuring it outside. That's to the left even, that's measuring it outside our heliosphere. Anyway, so we had to fit all that. So what we are coming out with in the next I think 2 months, is something called GAL-MC, which maybe many of you will be able to use. It actually predicts, it allows, one of the complications is that diffusion is actually anisotropic. All the previous models just assumed uniform diffusion and took that as a parameter, but actually the diffusion depends very much on the overall coherent field, so you have to model those collectively, and we have a ultra-fast new calculator that can allow for anisotropic diffusion. We'll come out with a random field model. We're learning the coherence length of the random field model. This is going to be replaced, finally, and then these are things I'm working on currently. Whoa, shoot, I didn't
Let's thank
calculate my
Glynis.
time.